And in offline, how many same participant or different participant?
No, the same participants
Okay.
who are attending in the online sessions. They are only allowed for the offline sessions, sir.
Okay.
It's a
Very good.
continuation of the offline. So,
Uh-huh.
basically, they are actually this time, asked to conduct both online and offline. So
Very
one
good.
week is online and second week is full of offline.
Yeah.
So totally 6 days is online session and 5 days is offline session.
Very good. Very good.
Yeah. So a lot of things we need to do in offline session. Yes,
Yeah,
sir.
offline things, you have to arrange all the things.
Yeah, definitely, sir.
So I will go very in general, like only overview only. So maybe the participants have not much issue. So I'll touch all the things,
Yeah,
and
yes, sir, yes, sir.
also it will be in general only.
Yeah,
So
definitely, sir, definitely.
in my research work also, like in bioelectrochemical systems, you are need electrochemical engineers, electrical engineers, mechanical fellows, electrochemistry, and biochemical.
Yes, sir.
So
Comparing team, you can start now. Divya?
Yeah, am I audible, sir?
Yeah, you are well audible. Proceed now.
Every sunset begins with it the promise of a new dawn. Good evening, all. As we completed our inaugural and day one session of our faculty development program, it gives me immense pleasure to welcome all faculty participants to the second day of this phenomenal event. The wonder of teaching is watching caterpillars becoming butterflies. Now, I would like to call upon Dr. M. Gopinath, Associate Professor of Department of Biotechnology and Associate Dean of Institution's Innovation Council, who transformed our young students into brilliant scholars. I invite you, sir, to deliver the welcome address.
Thank you, Divya. Respected faculty participants and beloved my colleagues and today's speaker, Dr. Suraj sir. So good evening, one and all present here. On behalf of the Well-Tech High-Tech Dr. Rangarajan Dr. Sakunthala Engineering College and Department of Biotechnology and Chemical Engineering, extended my warm welcome for the day two, faculty development program on waste to wealth, emerging trends in sustainable development. I mean, emerging green energy for sustainable development. So the program is, the faculty development program is, sponsored by ATAL AICT Academy, and on behalf of my own and the my co organizer Bharat Raja sir and the Department of Biotechnology and Chemical Engineering. So you are all welcome for this day two session. So the day two session is definitely is a very interesting session. So we have the eminent guest with us from the NIT Warangal, who is working in the Department of Biotechnology. So on behalf of the participant and the college, so sir, welcome you sir for this second day faculty development program. So thank you for giving this opportunity. Over to Divya.
thank you, sir.
Yeah, thank
And even I also conducting one FDP program now. So and Gopi sir is also with as a participant. So sir, I request you that you can also share my link of conference to the all participants. So who are free in the day, they can join that also free of cost.
yeah, sure, definitely sir,
Yeah,
definitely.
yeah. So already 2 days are left, but still we have 3 more days are there.
Yeah,
So total we are having around 22 lectures. So
yeah.
12 lectures are remaining.
Yes, sir.
Tomorrow morning, 10 to 12, we have very good lecture for how to basically for teaching only.
Yeah, definitely sir,
With this
definitely.
two subjects, so please you can share the same link to with them also.
Yeah,
And okay, so good evening to all. And I know this time is very odd for you also, even for me also. And we are just free from 5:30. But anyway, I am Dr. Suraj, and I had my PhD from IIT Delhi.
sir. Uh,
Okay.
so there is a guest speaker introduction is there.
Oh,
I will
sorry.
just
Okay.
I think Sangamitra, please introduce the guest speaker.
Now, I would like to call upon my fellow classmate, Ms. Divya M., to introduce today's guest speaker.
Thank you, Sangamitra. Dr. Surajban Sevda completed doctoral degree in 2013 from Indian Institute of Technology, Delhi, India. Is currently an assistant professor at the Department of Biotechnology, National Institute of Technology, Warangal, India. Prior to this, he was a scientific officer, research scientist at IIT Guwahati. He has published more than 35 articles in scientific journals and 25 book chapters. He received his Bachelor of Engineering in Biotechnology and Masters of Technology in Fermentation Technology from University of Rajasthan and Institute of Chemical Technology, formerly known as UDCT, University of Mumbai, India in 2006 and 2008 respectively. He was a visiting scientist at University of Calgary, Canada in 2018. Its research experience lies in industrial wastewater treatment, biofuels and bioenergy, life cycle analysis, metal recovery, biosensor development, green chemistry, and microbial electrosynthesis. We are proud to have such an honorable and an eminent person as a guest speaker today. We welcome you, sir.
Thank you, Dr. Divya, for such a nice introduction. So, okay, already we are late, so we're starting with this one. So, basically, see, wastewater treatment, see, when we see the now our society, India have now 130 crore people population is there. And when we see day to day, also see one person. So, you are from morning starting with our daily like bathing, also washing, kitchen waste, domestic waste. So, we can see how much wastewater we generate. And in India, now the things are moving well, and you can see all the metro cities have the proper planning. And even now, see when any new building is coming, say apartments are coming, so they have to take permission for okay, what they going to do with the sewage, and all the things are there. So in today's my talk, basically, so time actually in the starting it was the 2 hours, so now we are going to have 1 hour only this one, and 1 hour we have another lecture. So I briefly want to basically there are two ways. One is without air, one is with air. So without air we say anaerobic when oxygen is not available, and secondly we have aerobic when oxygen is available. So again, both the techniques are there. So I'm going to touch it. And third part, that is my research area also. So time allows, I'm going to touch it. Either you have my email ID also, and we are also tomorrow morning I going to link to sir. So in that one we have 12 more lectures, so you can join free of cost in that one. Okay. So so normally you see this plant. So you can see underneath here. One second, I just see here. One second. That. Yeah. So this is, you can see, underground anaerobic wastewater treatment. And see now that cost of the gasoline is very high. And if you recall, India have after Brazil, the second largest plants of anaerobic wastewater treatment plants. And if among the states, Maharashtra have around 50,000 units in the villages also. Also, you can see here. So these are also, you can see the plants here. So basically, they are treating the wastewater and getting biogas, or we can say methane gas. And this methane gas, as like we have LPG, the same claim is there. Even the some heating value is less, but that can be used for cooking, also for heating, and for other things also there. So this is the typical wastewater plant that we are having. And nowadays in CNIT Warangal, we have plant is there. And so I think in Veltech also they have more than 10,000 students are there. So maybe they also have and respective colleges. So this is the basic, you can see the figure of the plant, how it works. So when we say anaerobic, so see normally, see we have domestic wastewater, we have industrial wastewater. So all the things say kitchen waste is there. So all organic waste, if I say organic waste, it means carbon compound will be there. Okay, carbon is there, say glucose. So glucose we say C6H12O6. So whenever so normally you can find this carbon, hydrogen, and oxygen. See, when we go to a market, we have bread. When we say if you eat rice, so all have this multiple molecules will be there. Say glucose, maybe one item, two item, maybe 10, 100 carbohydrates or more. And so basically what happens, this organic waste come in the water. And water is the universal solvent. And normally in wastewater, 99.99 is only water. Whatever that we have to remove, that is the 0.01 only. And this 0.01 percentage, maybe most we have organic waste. Suppose this is some industry, they are say battery industry. So in that case, maybe we can have heavy metals also. Say pharmaceutical industry, maybe we can have some genobattery compounds also. Maybe some pesticide industry is there. And then, so here in digester, this organic waste easily can be converted. So in this one, when I say anaerobic, it means in that case, we don't have any oxygen here. Oxygen presence is not there. So then here, this one we going to treat here, and so I'm going to explain you more. So what happens here? So normally, don't be confused. See, we have multiple participants are there. So there are different things. Say we say anaerobic digester. We can also say this is the reactor. Okay, and also like I am a biochemical engineer, so I can say this is bioreactor. So bioreactor, it means you can control the temperature, pH, and all the things. So normally, also, so one thing you have to enter. Say when you're washing your clothes, so first thing what you enter the water. So in this one, we can also you can add agricultural and animal waste. We can use food waste. I think now I'm audible.
Yes, sir. Yes, sir.
Yeah,
Please proceed, sir.
yeah. My slides are visible. I think there was some
Yes,
issue
sir.
with
Yes,
the-
sir. Yes, sir.
Yeah.
There was some,
Yeah, actually, yeah, Wi-Fi is connected two computers together, so my screens will be so okay. So what happens
Okay,
here?
yeah.
So yeah. So see here we have the glucose molecule, and what we get here 3 mole of CO2 and 3 mole of methane, and methane we say 3CH4. So in this case, that both gases are useful. Even people say CO2, they don't like it. But CO2 also a very important substrate, I can say. It can be used, for if you see for going for any weddings, we have ice seals. They use CO2. Also in laboratories, they are buying CO2 in 3,000 rupees now. And also now my new research, we can use CO2 and we can produce C2 compound like ethanol, butanol, that is also there. So roughly what we are adding, all the wastewater things we are adding from this side, and we are getting biogas that can be used as electricity, as a heat, and now biofuel vehicles also coming there. And the remaining part can be used as fertilizer, blending, and compost. So briefly, I'm going to explain what is happening here. If you have any questions, you can ask me during the my PPT also, or also we can ask them later also. Okay. So what happens? See, normally, see the microbes. Basically, those who are not have any background of biology, but I think due to COVID now, everyone knowing what is the microbes, what is the virus, and other things. So okay, so even viruses also see without a virus also we cannot survive. So virus also some good virus, bad virus, same bacteria also good bacteria, bad bacteria. So bad bacteria we say pathogens. But here what happens? So actually this complex things we have 4 different kind of bacteria they are going to use. So see initially suppose we have glucose. So also say we have carbohydrate. So there in carbohydrate what we have, so this is the normal formula of the glucose CS2O. I put here N. So N equal to 6, it becomes glucose. For carbohydrate, we have 100 of kind of things they are attached together. The first thing they have the hydrogen bonds. Recall the 11th to 12th notes, we have hydrogen bond. So we have to break that bond. So for that one, and also see microbes. See now, when we eat the food, in our gut, we have around 10,000 different kind of microbes are there. And they all are healthy microbes. We need them. So then they're going to break down with the hydrolysis. And so I'm going to explain you more. And so normally, if you come to my laboratory, I have some posters that I love microbes. So microbes are very, very important things. So what happens is, suppose we are having, say, any wood, we have the cellulose, hemicellulose, lignin, and then, so this maybe some microbes here, and then you go to, these are high molecules, then go to acetate, getting CO2 and H2, and those bacteria, those produce methane, they call methanogens. So see, these are the basic things we are having. So see, this is the biomass. So biomass, normally we say when all microbes are together, and then see, we can get hydrogen, CO2, acetic acid, all these acids are there, and then finally biogas, that is have CH4, and also don't be confused methane and biogas. See, methane, if I say CH4 100%, if I say biogas, it means around 60% methane plus 40% CO2. So our commercial is if you have more purifying the CH4. So here we have first step acetogenic bacteria. They can produce they have hydrolysis. Then we have acetogenic bacteria. They produce acetic acid, and then we have methanogens. So this is how they look like. So basically methanogens. So in the oxygen-free, or we can say anaerobic environment, methane can be produced by a type of bacteria known as methanogen bacteria. So they convert this also, and here they need 37-degree temperature. There they can produce more, pH around 6.8 to 7.2. Okay, and they are very extreme bacteria. So see, if I compare the two things, anaerobic means without oxygen, and second part I want to say aerobic. It means we need oxygen, and then these are the basically the reactor that we are having. So we use, so breaking down of organic matter. So what we are adding inside, say glucose is there. So glucose is carbon number is C6. And what we are getting? CO2, 1 carbon, CH4, 1 carbon. And then biogas, so produced by microbes and contain normally 60 to 66% methane, rest is other gases, mostly CO2. And then, so this is a closed vessel, so then you can control the things. So also in that we have a sludge, also we're going to produce. So what is sludge? So basically, settleable solids separated from a liquid during the processing, and you can found on the bottom of the reactor. It looked like blackish also, and like I think now in till 2000 there was no norms for sludge. For suppose after sludge they can put it anywhere, but now norms are there. And the sludge basically what we are having maybe that have organic and inorganic compounds. In that one, sludge also have some oxygen demand. Also have some smell, odors is there. Also have some nutrients. Also have some pathogens. Maybe suppose if your wastewater comes from hospital wastewater, so some pathogen will be there, and so that should be very, very careful. Also, mostly have water in that one. So also, but why we need treatment of sludge also to stabilize the compounds available in the sludge. Also to estimate the odors, because if you put it outside, see normally what happens now when you go to near any domestic wastewater flowing. We can feel properly, destroy the pathogens, and also the reduced amount of solids, and also enhance the dewatering process. That's why we need the treatment. So type of digestion basically we have biological. So bacteria already explained aerobic and anaerobic. Both have different kind of bacteria. Some bacteria they survive only in presence of aerobic. Like humans also we need oxygen to our survival. Some bacteria they don't like oxygen, but they need some other electron receptors. So they use the free oxygen in the atmosphere, and anaerobes, no free oxygen required. So briefly, I'm going to explain some physiochemical mechanism of biogas production in the anaerobic digestion or anaerobic bioreactor. So see, basically biogas, when we are producing, what is biogas? Basically mixture of methane and CO2. The properties of biogas are similar to what we're going to use in our kitchen LPG. And biogas is also a common name for mixture of gases released from these bioreactors. So basically it has around methane 50 to 75%, CO2 25 to 50%, hydrogen 5 to 10, nitrogen 1 to 2%, and some H2S is also there. And this is you can see here total this current flame you can see properly, and maybe you can see or any municipalities or any villages, maybe you also have some plants will be there. So methane is a valuable part of biogas, and biogas that contains about 60 to 70% of CH4 has a calorific value around 6 kilowatt per meter cube. So that we can see around half, and so this is very useful energy is there. So basically, we have 4 stages here. Initially, see, we get in that our initial wastewater in the solid that have, see, kitchen waste is there. So we have a lot of carbohydrates and fatty acids are there. Firstly, so see, this all glucose molecules, they are bonded to the hydrogen bond. So firstly, we have to break that bond. So for those enzymes produced by microbes by the hydrolysis. So we can cleavage of chemical compounds through the reaction with water. Next slide, I'll also go to see with table also, so we have a good idea. Also, the insoluble complex molecules are broken down to short sugars, fatty acids, and amino acids. Then second step, we have fermentation. So also, it's very important thing that same microbes, all microbes stay together in the one reactor only we are having. So here, the products from hydrolysis are transferred into organic acids, alcohols, CO2, hydrogen, and ammonia. This hydrogen is actually H2, okay, not H. And then, so this is acidogenesis. Next, you have acetogenesis. In that, we're going to produce acetate. So these organic acids and alcohols are converted into hydrogen, CO2, and acetic acid, and therefore oxygen is consumed. And also that's why now we have totally fully anaerobic conditions. And lastly, we have the methanogenesis when methane going to produce. So here also there are two. So see, you can see here we are having H2 and CO2. So one kind of bacteria use H2 and CO2. Okay, only H2 and CO2, and then they're going to produce methane CH4. So around 30% of methane produced from this one, and one kind of bacteria only using acetate, and they getting produced CH4 and CO2. So around 70% of methane generated by the acetic acid. That's why it's acidogenesis. And lastly, so in this step, so there are 4 steps are there. So also you have hydrolysis, acidogenesis, and then acidogenesis, and then methanogenesis. So this is the, if I say here, so what is our inlet in starting carbohydrates? Suppose we have chapati or rice or anything, kind of wastewater. Also proteins and waste. So firstly, we have hydrolysis. So say here we have 100 glucose molecules. So by this hydrolysis bacteria, they're going to H bond going to break it down from here, and we get in sugars, amino acids, and fatty acids. And then you have fermentation. So again, C6 to now coming to C2 compounds. Alcohol, so alcohol is C2H5OH, and also getting hydrogen, CO2, and ammonia. So this is second step. And then from here, we are getting acetic acid, CH3COH, and H2 and CO2. And last, we have the methanogenesis, CH4. So one beauty is that all different kind of bacteria stay in the same reactor, and we are able to produce this one. Fine. So also the title of the design of the reactor, and also we have a lot of civil engineers, other things also there. So basically when we design, so see basically see how much our intake and how much, see suppose a society is there, they're producing per day say 20,000 liters of waste, or so depending on see how much our intake is there. So firstly, very important sizing of the reactor. So in that one, what is our substrate or feed rate, depending on that one, okay? Then we need some background information, particularly what we need what type of substrate, maybe you have kitchen waste, more organic compounds, domestic waste, and industrial waste. So we should be very clear what we are putting inside. We should know carbohydrates or fat, or that we should know how much is there. Then the type of substrates also is available to like 12 months, only for 4 months, 6 months. And then also the conditions outside. Suppose now I'm in Chennai, and now I'm in Warangal, my hometown is Jaipur. So now Jaipur temperature is now around below 10 degree, but in Chennai should be around 25 degree. So what are the conditions and locations where we are going to set up this reactor? So depending on, suppose here we are looking 37 degree. So in Chennai, 12 hours or 12 months is easy to maintain. But if you go to say Himachal Pradesh, Simla, or any colder area, so in summer, even in winter, we have to spend a lot of, either we have to shut down your plant in the winter, or either we have to spend a lot of energy to have the temperature. Also, what is average temperature there? So these are the factors that we need to, so when we go to design the reactor. So all those things are required to decide a particular size to handle certain amount of feed. So because feed we know, okay, how much population is there in industry is there, that we know properly. Okay. So simple. If I say so, anyway, fish stock entry into first reactor, then second reactor. So I'm going to say go to next slide directly. See, this is the reactor here. So now only one reactor. So to improve the things, now we have two reactors also. So first three reactions: hydrolysis, production of this acidogenesis and acidogenesis. First one reactor, and lastly methanogenesis. We go to the second reactor. So see, you can have waste feedstock reactor one. So also we can store the gas purification here. Also the biomass that can use for fertilizers. So what we do here: solids, carbon by nitrogen ratio, temperature, and pH and time. Retention time. Suppose it take 24 hours, 2 days, 5 days, 7 days. So again, this is also very important. I will also explain with some example to you. So see, this is the normally see if you see CNY ratio, very important. How much carbon is there? Suppose we have materials like dry rice straw around 67 to 1 ratio, dry wheat straw, corn stalk, fallen leaves, and so on. Also, we also so solid CNY ratio is around 20 to 31. Temperature is 25 to 35 degree, pH 6.8 to 7, and time we can also go 60 to 90 days also. So in that we can add some daily and we can take. Okay. And for mesophoric digestion, it is less than more than 20 days when temperature is low. It takes more time. So on the basis of background information, under certain conditions to handle, certain amount of waste will be discussing how to get the size of the reactor. So I'm going to give an example to you. So see here, so this is the reactor. So when you design the reactor, so we have 4 parameters. So here, top, because gases go upward. So here the collection one, okay, gas collection volume. Then this is the gas storage volume. So here you put someone and like when the gas we can store. Then this is the active digestion volume, and lastly the solid sludge volume. The total volume will be V collection, V gas storage, V active digestion volume, and then V sludge dash. So this will be total volume. So there are some thumb rules also there for doing. So it's, when it's under operations in the process, this type of phenomena will get inside, or zones will get inside it. But if you think about the reactor dimensions, or objective is to get the dimensions of reactor. So that also example I am having my example. So I will going to explain. So see here. So when you design the reactor, so again, it's total you can see like as Gopi is saying, some people mechanically is also there. So see when you have it, so we are seeing here H1. So starting even volume of the top head, volume of the bottom head, as the surface area of the top head, surface area of bottom head, volume of cylindric part. So whatever we did in the engineering drawing in the first year, maybe all. So all things you're not going to utilize properly here. So that only happens when we know how much volume we require. 100 liter, 500 liter, 1 lakh liter. Okay, then we can design properly. Okay. So this is the different parameters we came through, which can explain the geometry of this unit. So we have V1, V2, S1, S2, V3, R1, R2. Okay, all the things we can have. So if you know the type of the head present here, so depending upon the head type of the expressions will be different. So again, so normally what we do here, see R is here. R1, the characteristic diameter of top head and bottom head. So by this one, we can easily help. See, this R is also there. R is the radius of the cylindrical part. So 3 R we are having. So easily we can make the reactor properly. Okay. So now moving further. So see here also comparison between cross section and dimension. Again, we have the first one I discussed 4 volumes, and then also when you want to design V1, V2, V3, R, V2 are here also. So thumb rules we say. See, V collection and volume. So normally collection volume should be less than 5% of total volume, and VSL also less than around near 15%, and collect the gas storage and digester around 80%. So this is the reactor volume, and also storage. So this is the normal thumb rules are there, and suppose this is the other fellow some also software is also there. So when we need the where K is the gas production rate per meter cube, say like how much gas rate per meter cube digest volume per day. M is, so this is the K here, you can see how much the volume required. M is the gas production rate per kg of the total solids. So depending on, suppose we have more organic waste, we have more gas also. So depending on that one, we can also design these things. Okay, so this M and K also should be required. Suppose Bangladesh, K is around 0.4 metric cube per metric cube a day, and M is 0.28. Some studies they can count data. So in this one, we can totally design the reactor. So this is I discussed with the anaerobic reactor. Now coming to the aerobic reactor. So aerobic reactor is compared to faster than anaerobic, but since these are the big reactors, so the cost is very high here because we have to spend oxygen or air. Like see when you go for your like gas filling in your car, so see when the compressor is there. So we need compressor like very big compressors are there. So normally as aerobic, so this is the bacteria. So oxygen is also required here. In last case, it was not required. Then organic contaminants, nutrients, and here we have more thicker cells and more cells. Again, water and CO2. So if I write the equation here, so we have C6, suppose C6, S12, O6. Now we are having oxygen also here. Okay. So now what we got here, we will got only CO2 and water. 6 CO2 plus 6 S2. No methane will be here. So the commercial value of CO2 is also less, but methane has commercial value. But it is more faster reaction than some kind of compounds, say nitrification. If you want to remove some nitrate or ammonia, then we need this kind of system. So here, see, I'm in one stage here. So see, I'm comparing both the systems here. So I also one term named COD, that is the chemical oxygen demand. So basically total how much organic and compound is there in the wastewater. And COD is a parameter. Say suppose when you're working somewhere, okay, what post you are having, how much salary you are earning. Similarly, also suppose COD is less, it means water have less pollutants, water will be okay. And also we have a simple pollution control board. Respectively, we also have the state pollution control board. Every state have that one. So particular industries, they have the limit. Suppose we have an industry, say, I can see Sangeeta is here, Sangeeta Gandhi is there. So maybe Sangeeta has some industry, maybe a pharmaceutical industry. So for them, they say, okay, we cannot go with only 100 ppm, 100 ppm parts per million. COD only we can go out. So it means our intake COD say around 1000. So it means this 900 we have to remove. So for example here, so suppose same waste we are putting in both, 100 kg COD are putting here in aerobic, 100 kg COD in the anaerobic. So in aerobic we have to spend air also. So for air I need 100 kilowatt of air cost is there. So I'm getting here CO2 and nitrogen, and so removal is say 2 to 10 kg same time, say 5 days same time, and sludge is 30 to 60 kg. Again you have to treat the sludge also. While in anaerobic there is no requirement of air. So here we are getting biogas 35 meter cube, and that is helping us 285 kilowatt out. You can see we can have some revenue here, but same time is slow process compared to aerobic. See here we have 2 to 10 CO2 removal, so almost see you can see around 90% is removed, but here only 90 to 80%. But here sludge is also less. But compared to this is slow process, but here this one is not there, and we have this one. So depending on what process you are having, we have to choose in between the both processes, aerobic and anaerobic. Right? Now move back to aerobic. So aerobic, this is the normal, we have activated sludge process. So we are putting the raw water or say wastewater. Okay. Also air is given here, air is contained. So after all the microbes are here, then we have a settler here. So the treated water can go from here, and some microbes we can also recycle here, and also sludge coming down from here. And so also again I compare here. So see, we can also use this wastewater, organ waste. Now also you can see when you see in a pond, it looks so green. No, the algae is there. So algae actually very good. One thing, they use CO2 as a source, like plants. Plant, no, what plant do? Plant, if you see, plant need what? They need CO2, okay, plus sunlight. No, they don't need CO2, sorry. No, sorry, one second. They need CO2, sunlight, okay, and what they produce? They produce CS2O. It means glucose or any other compound. Plus, they produce oxygen also. All the plants, okay. Same things in macroalgae also, they're using CO2, putting oxygen, and this oxygen can be used, also they need light, can be used by the bacteria. And so that's why now the new research also combining both things together properly. So now we have, see, this is organic waste oxygen bacteria, they're putting CO2. The CO2 can be utilized by algae. So again, we can reduce the CO2 level in the atmosphere also. So both things collectively say biorefinery. So that we'll be able to discuss in the next lecture when we have one more special lecture for this one, 7 to 8. So here also see some ponds. So see we have the sunlight is there. So maybe naturally we have two zones. So top floor we have aerobic zone when algae also produce oxygen, bacteria is there getting CO2 and ammonia and PO4. So also see when we remove phosphorus, nitrogen compounds, then we need aerobic. Okay, and some anaerobic zone we have CO2, methane, all the things are there. So again, this is the oxygen, aerobic bacteria. So more biomass, more CO2, more water in case of the aerobic. Also, see when we compare the both process aerobic and anaerobic, what kind of things can be done. So starting with aerobic, so non-degradable things going to go to oxygen. You can getting cells, CO2, water, and here you're getting H2S, CO2, water, methane or biogas, cells, and also other things also there. Also see whenever see any reaction when we breathe also see what we go give back CO2. So see when you see the redox chart, so oxygen is the final electron acceptor that have redox potential of around 840 millivolt. Okay, so that's why all the reactions with oxygen they have high energy. So see there are two things also there. So some bacteria they survive only aerobic, some are anaerobic, some are facultative. So they are okay with oxygen also there, they can survive. Oxygen not there, they can survive. So for remove see here we get H2O2, NO3, SO4, iron. So depending on that we can go it. So again, if I compare all the microbes that present in the wastewater, so we have algae. So in that we have microalgae, filamentous algae. So we have the yeast, filamentous fungi, bacteria, we have aerobic, anaerobic, and facultative. Both fungi, again yeast, filamentous fungi. Protozoa also there and metazoa also there. So they are basically the disease causing things are there. So when I compare the bacteria, so I have aerobic bacteria and anaerobic. So aerobic require oxygen for their growth, anaerobic do not require oxygen for their growth. So in that also we have obligate, it means they cannot survive in absence of oxygen. Like say humans, we cannot survive in the absence of oxygen. So example is there, and some are microaerophilic, they survive with so lower concentration is required, so less than 1%, 21 to 10, 2 to 10%. Some example is here. In anaerobic also we are obligate, so this bacteria cannot survive in the presence of oxygen. So when oxygen is there, they cannot work. But facultative, they can survive. Also we have aerotolerant bacteria, they cannot use oxygen for their growth, but they can survive. And this is, if I say metabolism, what happens here, what oxygen is basically doing. See aerobic bacteria, so see oxygen go into metabolism, so they produce toxic products like O2 minus, OH, O2, H2O2, and then they have detoxifying pathway will be there. So production catalyst is there, and then they have non-toxic H2O2. What happens when oxygen is given to anaerobes? So here in oxygen, they have this pathway to detoxify this one. But in anaerobes, this is not available. This is not available. Okay. So someone asked, okay, what happens when you put oxygen in the anaerobic? So they use the oxygen, but they have toxic. See what happened to us also. See in our body. See when we breathe. So I've had again oxygen going to mix with the blood and going to circulate. Same thing here. So it's very important here. So when oxygen go to this anaerobic, so they get these products, but they are missing this non-toxic pathways. So that's why the death will be there. But in aerobes, these pathways are there. So lastly, they're getting H2O and O2. So they can survive. So now again, one example I'm taking here, activated sludge process to treat the wastewater. So again, removal. So also one more thing here in the process, suppose a genovatic compound is there. Genovatic compounds are those compounds, they are man-made. Say we have this all pesticide and all the things. So either what we do here, so either they become less toxic or non-toxic. So I'll give some example here. So this is the process that we are having, aerobic process. We are putting, sorry, 1 second. Hello. Yes, actually I'm in a meeting. Anything urgent? Okay. Okay. So, OTP. Okay. Gopi ji, was 2 seconds, sir. ऐसा लिखिए 564188. Yes, sir. Done. Sorry for that. I got an urgent call. Okay. So here we are putting wastewater here, also giving the air. So normally air you give in the bottom, and there's when you design the so how much bubbles we required, all the things here. So air go off, to provide oxygen and mixing, and then primary effluent we are entering from this side, and we are getting this ML/SS mixed liquid suspended solids, and then we have secondary clarified, and then we get the secondary effluent, and properly we can also recycle. There's some bacteria here, so this process, some bacteria around 10% we can recycle here. So at least when the new water is coming, so that's why it's more faster process compared to the anaerobic. And here the solids we can find from here. This is, you can see here example. The aeration tank is there, so effluent is coming from this side, sludge is here. So this is mixing properly, tank is there, and we can secondary clarify like this one. So this thing, when we go to any sugar factory and other thing, I'm sure maybe you've seen this thing kind of things. So PC also there. So this is the typical bacteria that having, and bacteria diameter. Anyone how much? What is the diameter of bacteria? So bacteria have very we cannot see with our eyes. So 1 to 3 micrometer, 10⁻⁶ diameter they are having. Single cell, only single cell. They have capsule, cell membranes, and they are very effective. All kind of enzymes they produce. So what happens here in wastewater? So this is the wastewater. So normally, if I took one course for civil engineering, so I say this is the food for microbes. Okay. So when this is a cell, there are membranes. So see, any wastewater, so glucose molecules are there. So again, these molecules have to go inside the cell by diffusion. Also, oxygen also coming from that side. Okay, or absorption. And then we are getting ammonia, CO2, H2O, and also more cells, more thick cells. So we're getting new cells also, and also we have slime layers on the surface also. And see, also the particles will be also there inside. We have enzymes also there. So this is the normal typical bacteria I'm saying to you. And this is when you see in the picture. So this is a mixed liquor. Also we have fluorescence, a process of contact, and addition of where the particles of dispersion from larger size. So they also be clusters, like granular-like clusters. And again, our aeration tank is here. So absorption and adsorption going to happen here only. And you can see the secondary clarifier is required. So again, what is our things? Our influence coming screening is there. Suppose some plastic things are there. All we can remove from here. And then our primary clarifier will be there. We have filter will be there. Then we have this process properly. Also we recycle here also. And you can see that's the main thing doing with the bacteria. I hope it is clear to you. So basically 3 steps are required here. So first one, transfer of food from wastewater to cells. If I say food, it means whatever the content is there in the wastewater. So see, this is our cell, typical cell we are having, one cell. So any glucose molecule is there. So that firstly go out inside the cell. And then for that one we need advocate mixing, also give more time to them. Okay. And then secondly, when cell go inside, so conversion of food to new cells. See, bacteria divide very fast. See, E. coli divide in 21 minutes. Okay. So then we have this biomass, also diesel oxygen level is also there, and also suppose some nutrients are missing. So we can have carbon, nitrogen, phosphorus by 100 to 1. And then we have flocculation and solid removal. So we need proper mixing, proper growth environment, secondary clarification is also required. And this is the bacteria, we can see how it look like. So again, this is our so what are the control factors we are having? So one is, what is the load we are adding? See, okay, we cannot put 1 lakh COD. So that also air, biomass quantity and age, the diesel oxygen levels, also the hydraulic load and solid loads, settleability, also sludge blanket depth, how much sludge is there. and also how much is recycling. So these are the control factors that we are using for here. Okay. So again, so suppose like faculties are here. So suppose we do some little exercise. So organic load, it means how much, per, see what happens, how much, say kg, how much carbon kg per day you are putting. So by say pounds of organic content coming in the tanks. So say in one day, how much you are putting inside. So this is here. Second thing now is actually there's a big lecture I'm skipping here. Secondly, suppose we have ammonia kind of things. So here actually very, very important things here. Till now, they need the oxygen. NH4 to NO2 or NO3, nitrification. And from here, oxygen is not required. So what happens, see this is the surface here, so they make biofilm, okay, like this. So this biofilm more thicker. So oxygen is say only this level only here. So here these three things going to happen here, in the outer layer. And inside when oxygen is not there, then they convert NO to N2 and then N2. So how they do? Nitrification required oxygen, and this is oxygen not required here. So we're getting NH4 to NO2, or NO3 to NO2, NO and N2, N2. So nitrification converting ammonia into nitrate or nitrite. And examples bacteria, nitrosomonas and nitrobacter. And then we have denitrification, NO3 to NO2 to N2. And this is also very required and also happen in the aerobic. So examples of microbes, pseudomonas. And here also we have some kind of reactors, anoxic denitrification zone, aerobic. So here both are required. Anoxic also required, aerobic also required. Aerobic required ammonia to NH4 to NO2 and NO3, we need aerobic. And then NO2 to NO, N2, NO, no aerobic. So this is called nitrification, this is called denitrification. So I'm skipping here. So these are some examples we are having. Like say substrate availability, oxygen concentrations, reduced carbon. So nitrification, we have ammonia, urea, amino acids. And so this is the first one. Denitrification, we have NO3 also, NO2 also, both can be used. Okay. Oxygen concentration, is starting very high, here we have low. Then reduced carbon, no effect, here we have high. Moisture required, also here. So pH less than 5, and also lower than 5. So by this one, I am finishing our first lecture. If you have any questions, let me know, we can discuss. And also please join me for tomorrow. And Gopi sir, if you have any questions, they can ask us. And then we have 10 minutes break. And then we want to start our next lecture.
Yes, sir. Yesterday we didn't give you any break because inaugural session followed by the guest speakers session which started.
Okay.
So no issue, sir. We can take the break for 10 minutes. So and again we will join by.
Yeah. So if there are like one or two questions, I can able to answer.
Yeah, definitely, sir.
And I think next lecture is more easy compared to the best part because that is biomass and energy. So I think that is more interesting for you.
Yes, sir. Definitely, sir. Participants,
Yes.
you can feel free to unmute yourself and you can interact with us about the first session.
Please introduce your name and your college, and then you can please explain. And tomorrow you have to join my workshop also in the morning. So there you also can interact more.
Dr. Suraj?
Yes, madam.
Yeah, thank you, sir, for an excellent session. I'm Krishna Veni from Department of Microbiology, PSG College of Arts and Science, Coimbatore.
Okay, madam.
Yeah, so you gave a detailed presentation on both anaerobic digestion and the wastewater process with aerobic treatment, sir. Thank you so much. I have a few queries. One is there any work which is done on poultry wastes for anaerobic digestion?
Poultry based, actually what happened, madam, actually I see, I am teaching one course, green technology.
Okay.
So in India, actually every state government, especially in 90s and 2000. So when LPG was not available till 2000 easily, okay, quota was there.
Yes.
And now the things also, that time there was a program, National Biogas Program. Okay. So in that one, whenever we make, now we have toilets program is there, now we can, some subsidies there.
Yes,
so
sir.
that time, for small farmers, when suppose I have some cattle, a cow or buffalo is there. So that time there was a plan, and every panchayat they give some funds are there. Even I also have a plant to 90-80s at my house. And in India, I think Maharashtra doing very well in this one. They're having around 50,000 reactors, and small reactors. So what happens here, see, normally with anaerobic, compared to aerobic, very cheap process. And when it started, so that's why they have all these small reactors underground. So temperature should be okay there. And in that, depending on the volume, so kettle pit can be used properly, no problem in that.
No, poultry waste, sir. Is
I mean, poultry waste also, no problem.
okay. Okay.
But poultry waste actually have more demand for, especially for vegetables. So that's why this goes sold more high rate on the market. So small farmers, they do vegetable farming.
Yes,
They
sir.
need this fertilizer, like whose demand is there.
Yes, sir.
Yeah.
So you said the anaerobic digestion requires 5 days. Is it for the overall acidogenesis, acetogenesis, and methanogenesis, or?
No. Actually, see what happens here. Suppose directly if you give glucose, suppose normally what happens, I choose one scenario when we have complex wastewater,
Yes,
starting
sir.
carbohydrates. So say where we have thousands of glucose are there. So even one very good thing with wastewater, we are using mixed culture. Okay. So in the starting, those bacteria only active. They have the hydrolysis enzyme going to break down the only H bond only. And then we have fermentative bacteria, then we have this acid production bacteria, then lastly methanogens. So normally it go to for 50 days also the starting. But when a process started, and now see I also spent now 2 reactors also there. So even when after 50 days, we can also operate in continuous mode also. No, even I see in some plants like this also. But even compared to aerobic, it's slow process. But here also you have to spend less money and get some more profit also.
And regarding one last one, sir,
No.
regarding the aerobic treatment process, the sludge waste which is obtained after the secondary clarification process, can that be taken back to anaerobic digestion, and
Okay.
can it be
Yeah.
continued with acidogenesis and
Yeah,
until
actually,
methane generation?
it's a very good question I can say. See, normally when we say sludge, so basically sludge also have lot of this organic microbes also there. Okay, so all these microbes are aerobic in nature. So and also some, see, we have say unfermentable sugar. So that sugars are very like sorry, one thing I can take call.
Yes, sir.
One
Please.
second. Hello. एक मिनट 1 second. OTP is 813-329. 329 813-329. Thank you. Okay. So actually, where I forgot where I was.
Sir, it is regarding the use of sludge from the aerobic process into
So actually,
anaerobic.
so we have one is like more aerobic cells are there. Second thing, what we have, like we have some sugars, they are very complex sugar. Even they are not able to consume in aerobic also. So see, when you go to any Western world, if you go to European things, especially in Netherlands and US, so there in India, I think still also not so strong law is not there. But there, what they do, this sludge, if suppose some pathogen is there, they actually burn this sludge. Incineration is there. So that's the only, because sometimes what happens, suppose some heavy metals are there, some carcinogen is there. If you put in the field, then it come to again to our vegetables or say rice or so that will be come into food cycle. So the treatment is required, but we cannot keep in the anaerobic. That is not advisable.
Okay, sir.
So maybe you can go with incineration for this one, or maybe some other method.
Yes, sir. Yes,
Maybe landfilling or anything like that.
yes.
Sir, you were also talking about the nitrogen process during aerobic.
See, for phosphorus removal, for nitrogen removal, we have to go with aerobic only because of the mechanism.
Got it. Thank you, sir.
And
Thank you so much.
Yeah. Also tomorrow, if you have time, sir will share a link to you. When my program is going on, you can join in the morning.
Oh, thank you, sir. That will help.
Okay,
Thank you. Thank you so much.
So, okay, sir, we have 5-minute break. Sir, unmute yourself. Gopi, sir. You are muted.
Yeah, definitely, sir. Definitely. You can take, sir. No issues.
Yeah, 5-minute break is there, then I will
Dear sir and ma'am, so we will go for
Please don't, stay in the
5 to 10 minutes.
stay in the meeting
5 to 10
only.
minutes break. So those who wants to go for the break, you can go for the break. Others, in this case, no need to leave the meeting because it's the
Yes,
online
yes.
session and all recording is going on as per their guideline of ATAL. So again, we will join by 5 or 10 minutes back. Thank you.
I'm
Yes,
sharing
sir,
my
we can take sir 5 to 10 minutes.
second PPT. I'm sharing here, and then I'll go. No problem.
Yeah, definitely, sir. Definitely, sir.
Yeah. I think my PPT is visible.
Yes, sir. Yes, sir. Yes, sir.
Yeah. So okay, I'll go pour some water and come back.
Yeah, sure. Definitely, sir. Definitely.
Yeah.
So by the time, actually, we are planning to share with you all the two Google link. One is that the today's feedback link. Another one is the link is related to the some of the willingness we want to take you from the participant side. So regarding the transportation, hospital, accommodation, and then the lunch, we actually planning for both veg and non-veg. So so you can give your suggestion according to your willingness, so in the form, so that we will take it the consideration for arranging the food during the offline sessions. And yesterday I informed you all that there is a special gift is there for every day. So we don't want to disclose that who are that be chosen. So that will be we are monitoring based on the conversation that are taken place in the every session. We will recording it, and we will choose the one of the best participants in the everyday aspects. So at the end of the day, your faculty development program, that means validity session, so on 16th of December 2022. So we will give the the special gift to the selected participants. And the yesterday, few of the participants not registered their attendance and the feedback. So out of 50 participants, so only 35 have given the feedback and the attendance. So still the link, yesterday link is kept open for your the things to be done from your end. So I request every one of you, please fill out the form using the yesterday's link. And today also expected to you all to fill out the form without fail, because we are we are we are actually considering the attendance as per the feedback only. And secondly, however, we are actually taken the list who are joined the meeting. We are noted down. So as per the guideline of ATAL FDP, so every day I am marking the attendance in their portal. I think you may also see in your portal, so whether the attendance is updated or not in the yesterday session. And today also I am going to mark the attendance after the session. So hence, I request every one of you, please, fill out the form without fail. So whenever the a link is posted in the Google. So hence, I kindly request you all, please fill out the feedback form, and the feedback form only is shared with the Google chat room window only. And second thing, the willingness form also will be shared in the Google chat room only. So kindly be alert and fill out the forms. If any queries on the your end, any difficulties that are you come across during the session, please reach me, through WhatsApp or otherwise the Gmail, whichever the mode you are, convenient. So we will definitely sort out those issues our end. Sir, in a couple of minutes, the link will be shared with you all, sir. In today's session, one more session is left over. So probably another 2 or 3 minutes, Suresh sir will start the session about the ecological and economical aspects of biofuels and biochar. Still, the second half session will be there. So probably today expected time for completion of this session will be up to 9. So by around 8:50, we will post the link. Participants, if you have any, suggestions that is required from your end, unmute yourself. You can, discuss with me. No issues. Meena ma'am, you are saying something, but there is.
Sir,
audio is not.
will you share the presentation, sir?
All the presentations, we will planning to share with you all, either by the, Google Drive or otherwise the other planning also, we are working on it. So we will let you know, ma'am, about the method of sharing and the things. And definitely we are sharing all the sessions, PPT, and also we are planning to release the souvenir on 12th of December. So the copy of souvenir also will be shared. So
Yes, thank you. Thank you, sir.
yeah, definitely. Actually, no, ma'am. There was a question in the chat room. Gopi, Chitra, ma'am. I think when you apply this FDP itself, you can see the both the online and offline in the window. So the criteria is for the FDP is you need to meet 80% of attendance. So all together, the online session is almost 50% of attendance, and the remaining 50% attendance from the offline mode. So altogether, the participants should meet the 80% of attendance. So in that case, so it is mandatorily it is required for the offline sessions. So we will give some of the like according to their academic schedule and the things is required for the faculty. So there is no doubt. So we will work together for how far the feasibility will be there in that case.
Okay, sir. Can we start now?
Yes, sir. Definitely, sir. Please, sir.
Okay. So actually, so again, welcome back, and also please note it down my email ID also. So if you have any doubt is there, you can also write to me. Also, Gopi sir also. So second talk is starting basically. See nowadays, if you see the last budget, see now in Delhi, what happens in December, especially near Diwali time, the air qualities go very bad. Why it got bad? Because see, the farmers they burn the paddy, all this waste biomass things are there because they don't feel that any economic value is there. Last budget, what they do? So normally in India, still we have more than 50% power with the coal. Okay, so now one concept came: can we firstly convert this biomass to some coal type, and then we can burn with the coal. And now DBT coal was also came, I think, in the last January, in the starting of the year, and this is also very good aspect. So today in this lecture, again our audience are from different fields. So very general, I would explain what is the biomass, what is what are the sources are there, how we're going to convert them as useful things. Okay. So see here also you can see this kind of farms. So normally see this team is there. So only we go with maybe rice or wheat. Mostly we have this mostly that happen. So all stay actually stay there only. So previously what happens we can use for cooking. Now LPG is available everywhere. There's more clean fuel is there. So what we do with this one? Okay, so now there are different technologies. Either this is kettle feed, okay, and now like with the new technologies, we can also convert it biochar, lignite, and all the things. See here also, so biomass basically also we have this is after the when after the farming and so also you can see here what are the things also here. So there are many sources are there for this one. So how to utilize it properly? Okay. See here, this one small parts are there. And traditionally, if you go to villages, all the things done by the small things only. So this is very useful. So what is basically we are having here? See here now. See if you go to any industry, big industry, they have a boiler. Okay, and normally industry, suppose especially biotech industry they need steam, and this steam can be used to produce electricity in the factory. Also say chemical industry they need temperature of 500 degree, 900 degree, 1000 degree. So steam is very useful for the industry. And so see every industry they use either coal, and now this kind of biomass can be used in this in the boiler as well. So now we see the cycle. So it's very interesting. So already I explained this our trees actually they make food for us, not only for humans and animals also. Without trees we cannot survive. And making this food, what they require? They require only sunlight, CO2, and water. That's it. Nothing else they require. Okay. And then in return they produce CS2N like any compound. So this is the normal formula of carbohydrate. When I say CS2O. So if I put N equal to 6, it becomes glucose. C6H12O6. So see here, presence of sunlight, H2 and CO2, they produce this one, and also they produce oxygen also. So see now we have missions in the Mars, Moon, okay? So there was a movie, I think here. So one astronaut was actually stuck there. So what he did, he have some seeds are there, and that fellow grown that one properly. How all vegetables are here. So see, this is the plant. So we have agriculture, forest. So one is very easy way to getting biomass from here. Secondly, say animals, they eat the leaves, all the things. And now we can see, now we are seeing organic farming. In organic farming, what they're using? All this cow dung properly having, that will also go. And even the animals, when they die also, that also come in the biomass only, livestock residues. Also, we have agro-industrial residues, and also we have the municipal organic residues also, like say, one madam asking about the sludge. So, this all come together in the category of the biomass. Here, so you can see the cycle. See now what happens now, climate is changing. Sometimes when rain was not there, now rain is coming that time. So first thing we have forestry, crops and residues, and then you have agriculture crop and residues are there. Sewage is also there now. Municipal solid waste is also there. Animal residues and industrial residues. So overall, combinedly we have the biomass sources, and roughly so we have from getting biomass from wood, also from garbage. Also that's why I again request you also please have awareness when in the morning municipal corporation vehicle comes. Please segregate your waste and solid waste, so wet waste, dry waste. So we have crops and also alcohol fuels and landfill gases also there. That also come in the type of the biomasses. So basically, what is biomass? So biomass basically refer to any organic material that are derived from plants or animals that is living or was living in the recent past. Again, I'm repeating. So basically, what is you say any organic material that derived from plants or animal that is living or was living in the recent past. So if definition say from we have from United Nations framework. So non-fossilized and biodegradable organic material originating from plants, animals, and microorganisms. That shall be include products, byproducts, residues, waste from agriculture, forestry, also related industries, as well as the non-fossilized and biodegradable fraction of industrial and municipal waste that come in the biomass. We can define the biomass. So normally, if you see classification of these fuels, so what fuels we are having? Now we can see this bioethanol. Now in India, when you see go to petrol pump, so now they're blending ethanol, blending C2H5OH with now petrol gasoline. And now I think target of 20% they are going to achieve in 2024, I think, I'm sure. It started before 15 years. So now they're blending this ethanol. Also we have biodiesel. So biogas already explained in the last lecture. Biodiesel when it comes, so what we are having here, see algae mass is there, triglycerides are there. So in that also we can convert to biodiesel. I think you had the name Jatropha. So they have seeds that have oil, and also the biomethanol fuels, chemical fuels. So this methanol, all are type of the biofuels. So now, if you see any wood, what we are having basically lignin, cellulose, and hemicellulose. That's why the wood is so strengthened. So here we can have physical treatments, chemical treatments, physiochemical, and also my focus on biological treatments. So what we have pre-treatments, we have hydrolysis and fermentation. So see, we have this glucose, xylose, urbanizers, other lot of things are there. And here we can have two kind of products: liquid products and gaseous products. So gaseous, we have biogas, biomethane, and biohydrogen. And now even ministry also have a lot of funding for hydrogen production. Much more clean fluid. And liquid, we have biodiesel, bioethanol, and ethers. Going to explain it soon. So basically, primary biofuels that normally say, okay, no need to see directly can use. See now, like we see last 50 years, we have a lot of changes are there. Initially, if you go see all the villages, we have use the wood as our for the cooking and all the things. So normal primary biofuels, like the natural biofuel, nothing required. We can use firewoods, plants, wood chips, forest, animal waste, landfill gases, crop residues. Directly you can use. Now, secondly, now we have third generation going on. First generation. So in that one, we are going to starting for the biofuel production. Say whether barley. See normally when you alcohol is produced. See with the wheat, barley, also potato, sugarcane, oil seeds, soybean, coconuts, and flour, animal fat. So in the first generation, only going to produce only the ethanol. So how to produce ethanol? So C6, glucose molecule is there, C6H12O6. Also here we have yeast. What we are getting here? 2 C2H5OH plus we are getting 2 CO2. So normally 1 mole of glucose giving us 2 mole of ethanol and 2 mole of CO2. Okay, so roughly 1 kg. Say if I say 1 kg glucose, give us around 0.49. So this is coming the first generation. Okay, then so first generation is very easy one. Normally like this substrate, say rice, you can cook it, and again you can have this one alcohol. Second generation, now more research done. So using bioethanol and biodiesel from the cassava, jatropha. See what happens here, say this potato, sugarcane, they're all coming in our food chain. Potato we need for our vegetables also need, sugarcane also required for the sugar. So, but now then, some countries, they don't have food also. Even wheat can also use here. So there was a debate there, why you are using the first, this food chain things are there. So now we can easily from like grasses also, wood also, we can easily have this one. And now the we can say third generation, so we can produce the microalgae, microbes directly. So now research also going on here also and here also. So we can say this is primary biofuel as it is in the nature, we can directly use it, and this is the secondary biofuels. Clear? So normally what we do, we have a biomass, depending on wood or anything. I already explained what is biomass. Then you have to decide a bioprocess properly. Suppose say cellulose is there. So how to remove cellulose to small molecules? And then we have two kind of fuel, liquid and gaseous. So liquid we have biodiesel, bioethanol, ether, gaseous, biogas, biohydrogen, which I already explained to you. So now again, if I again explain, so first generation, directly we have sugar and starch, plus bioethanols, conventional biodiesel production and biogas. Second, we are going more complex one and more waste material like cellulose, ethanol, hydrogenated vegetable oils, biomass to hydrocarbons, biosynthetic gas, and third generation bioil from algae. And even now in my research, I'm using one more new term that which is syngas or synthetic gas. So in that one, what we are having H2, okay, H2 and carbon monoxide. So there, with the help of the this is also gas fermentation. Okay. So actually, I submitted a project also, and now actually I'm looking forward to come the output, and we are, from here we can try to produce ethanol. Also, you can use CO2 also here. So this is the category that we are having here. So normal, if I classify the fuels, so classification is a very important means of assessing the properties of fuel, which fuel should be used when. The fuel belongs to a particular group, have similar behavior irrespective of their type of origin. So okay, we need a calorific value, and you can see the global also. Which country have the full control on the gasoline or any LPG or anything? They are now what is happening in the world. Some war is going on. So that's why a new biomass is considered as a for gasification or other. So we have also normal burning, thermochemical conversion. We can check its classification and then form the known properties of the biomass of that group. We can so there are three methods of classifying and ranking fuels using their chemical constituents. So we know how much carbon will be there, how much oxygen is there, how much hydrogen is there. So in that one we can classify this one. So one is we can go with atomic ratios. Second, we can go with the ratio of the lignocellulose constituents. And thirdly, we can go with the ternary diagram. To ternary diagram, I will explain you. So atomic ratio basically see we know how much carbon, what is the formula. So classification based. So that's why you see how much total carbon in that waste. So we can at least say okay how much fuel I have. Classification based on atomic ratio help us to understand the heating value of a fuel among the other things. For example, a higher heating value of a biomass correlate well with the oxygen to carbon ratio. It is from 25 to around say 0.18 to 1.03 to organic by carbon ratio. When the hydrogen to carbon ratio H/C ratio increases, the effective heating value of the fuel going to reduce. So we need less hydrogen in that one, and we need more this one. The atomic ratio is based on the hydrogen, oxygen, and carbon content of the fuel. So basically, we have hydrogen by carbon ratio, oxygen by carbon ratio. Also, whenever you see, if you go to any village, always when you burn the woods, you get the S also. So dry S-free basis for all fuels, from carbon anthracite to carbon deficient woody biomass. The plot known as also 1 Kelvin diagram shows that the biomass has much higher ratio H/C. So I will going to see in the figure to you. So this you can see here. So here we have O/C, oxygen by carbon ratio. Okay, and here we have atomic high H/C ratio. So you can see actually anthracite I think highest production in Telangana and Karnataka. So you can see this coal. This is very near here, more O/C. So that's why they have more energetic value. Then you have lignite. Then peat actually produced by the biomass. I will show the picture also, and you can see the biomass. So whenever it goes near here, they have the more in a calorific value. Okay, so biomass is also here. So again, here we have wood, lignin, and cellulose. So this is the formula that we are following basically for the large range of biomass. So whatever the biomass is there, again we put how much hydrogen carbon is there. So maybe express the linear function of the O/C ratio. So this is the equation we are using H/C by 1.4125 O/C plus this factor. Fresh plant biomass like leaves has a very low heating value because of its high H/C and O/C ratio. So already we also know see the stems and leaves. The stem have more energetic value compared to the leaves. The atomic ratio of fuel decreases as its geological age increases, which means that older the fuel, higher its energy content. Because the older the fuel, they have more lignocellulose and all the contents. Already you can see the trees also. So anthracite, for example, a fossil fuel geologically formed over millions of years, has a very high heating value, even compared more than the coal also. So lower H/C ratio of anthracite gives high heating value, but the carbon intensity or CO2 emission from also will be high. That's the problem with the coal. Among all hydrocarbon fuels, biomass is highest in oxygen content. So that's the actually oxygen, unfortunately, does not make any useful contribution to the heating value, and make it difficult to transform the biomass into the liquid fuel. That's why compared to that in the chart, the coal and all the things we are having. So the high oxygen and hydrogen content of biomass result in high volatile and liquid yield respectively. So how to overcome this? So high oxygen consumes a part of hydrogen in the biomass, producing less beneficial water, because when oxygen is there, S is there, H2 will be there, and thus the high HYC content does not translate into the high gas use. Say for example, see we have the leaves, okay? Fresh leaves, they have water content is there, you can heat it. When you dry this one, so again then water will evaporate, so even the total mass will reduce, but very going to increase. So one is we classify with the HYC ratio. Second, we can classify relative proportion of lignocellulose components. So this is also very, very important. Okay, how much lignocellulose we are having. So biomass also classified. So how much cellulose, hemicellulose, and lignin. For example, we can predict the behavior of biomass during pyrolysis from the knowledge of these components. So we have one figure 11, plot the ratio of hemicellulose to lignin against the ratio of the cellulose to lignin. So I want to see the figure to you. One second. See here. So we have the cellulose to lignin and hemicellulose to lignin. So this is the miscellaneous biomass, the woody biomass, also the herbaceous biomass. So here actually we are more comfortable here. So depending on how much, because all have different carbon content is there. Hemicellulose actually have the more, the cellulose has the more carbon. And lignin is again is more complex to break down chemically. So in spite of some scatter, certain proportionality can be detected between the two. The biomass falling within these clusters, we have similarly, so whatever biomass we are having, ratio is there, so we can easily find it out, category. So I'm skipping this. Then very, very important. Third is, we have the ternary diagram. So the ternary diagram is not a tool for biomass classification, but it is useful for representing the biomass conversion process. Actually, it shows we have three things like a triangle. One we have carbon, one we have hydrogen, one we have oxygen. So I'll show it's very interesting. So you see here, so this is we are having carbon here, okay? Here we have oxygen here. Here we have hydrogen here. So what we are looking for? We are looking for where we get more energy. So here, suppose in this part I will go here. It means here only carbon is there, okay? If I move toward this side, it means in carbon we are getting oxygen. See here in the middle, 50% carbon, 50% oxygen. Here, so 33% carbon, 63 oxygen. So when you're moving toward this one, the heating value is going to reduce. So here also, see here, I say here you can come coal, char, more carbon, char have around 90% carbon, okay? 90 to 95% coal. Now see we coming here, C2H4, CH4, one carbon, H4, and then in middle. So this part have more energy, okay? And see here, then again H2O. This line have low energy, oxygen H2. H2 are there, compared to H2, no energy compared to here, carbon not there. So this is also an in middle. So what is your ratio of C, H and O? So I think this is more clear to you. So we are looking for the, by easily we can, so if you got a new fuel. So we know how much carbon, oxygen, oxygen, and where they are here in the chart. They are here, they are here, they are here, they are here. Depending on the biomass is here, you can see it. They have more hydrogen, carbon, and this one. So this is how we can also divide or distribute. So depending on that, we can invest how much I have to invest. Clear? And second thing, I can say peat. Actually, incidentally, the youngest fossil fuel formed from biomass. And when you go to Western world in India, as you can see here. So this vessel naturally you can see plants are there, and then this is after you get dried, and you can easily this one. So the coal I was talking in the Union budget. So they are saying how to convert firstly biomass, this biomass to like coal-like structure, and then you can feed with the coal. Okay. Now come to the new concept that we are having, biorefinery. See, we have petroleum refinery, chemical refinery. So see here we have diverse kind of biomass. See also this kind of this fruit fields to the thermal. This one also you can see the this one. So here we can get fuels, solvents, bulk chemicals, plastics, fibers, phytochemical novels. Example: ethanol, biodiesel, acetone, butanol. This one. succinyl acid, sucrose, thermoplastic, starch, cellulose fibers, corn oil, and triglycerides. So how to do it? So basically, biorefinery concept, we are having biomass from the plant, this one. So household, we're getting S, they recycled. So we can go with biofuels, heat, electricity can be used, biomaterials. Also, say after the say papers are using, can we go back here? And here this, we can get CO2, all the things, and the CO2 also going to be used by the trees. And also here, companies are also putting CO2. So this is the total, we have to cycle is here, the carbon cycle. So this is a picture of this biorefinery, you can see here. So basically what we are doing here, see, we are using grass biomass. So grass, clover and nuisance. So we have sledge. Firstly go with pre-treatment and pressing. So press cake is there, you can get juice. Juice directly go for amino acid separation, then you get amino acid high grade, lactic acid separation, lactic acid you can separate, residues, and then this cake go to the AD process, already explained, anaerobic digestion, you're getting biogas, bio-CNG, and the pressed cake again we got fiber utilization, getting fiber, converts into liquid fuels, second generation biofuels can be quoted here. So this is one more example how you can go to use the biomass. Then again, biorefinery concept. So again, why we need energy? See, if you go to Western world, see now my brothers stay in Canada, my friends are there. So now they have minus 25 degrees centigrade temperature outside. So they have to spend a lot on heating. Same thing, see in our summer, how much we have to spend for AC and coolers. Biomass, first is a sugar platform, biochemical. Residues can be combined heat power. Also go clean gas, syngas that we are using CO and H2 to the fuels, chemical and materials. Also we get the conditioning gases after. So this is how the concept came. One second please. In this one actually this is totally interdisciplinary. We need person from mechanical, it was electrical, chemical, biochemical to design the process, to design the reactor, design the piping and all the things. So again, firstly, you have to decide the substrate, feed, and then what kind of technology you are looking for. See, we don't need all chemicals, but what are the chemicals available? And then you go to many products. Okay, and this is you can see the biorefinery. So we can find. So this is again if wastewater. You are getting effluents. So you can get algal biomass, pigments, carbohydrates, proteins, lipids. Pre-treatment we have sonication, microwave, enzymatic, hydrothermal, pulse electric. Then carbon data, we can do fermentation, we get hydrogen, methane, ethanol, lactic acid, enzymes, lipids. And when the lipids come, so here we have transesterification, you can get diesel and glycerol, all have same formula. And again, glycerol you can use with butanol and lactic acid. And again, you got proteins, so fertilizers can be waste. So all kind of waste can be used by this biorefinery concept. So basically here we have thermochemical conversion process. So in that one we have gasification process. So in that one gasification and pyrolysis. So in basically pyrolysis we burn without oxygen, we heat in without presence of air. In gasification we need air. So also we have catalytic steam gasification, biomass to liquid. Then we have fast pyrolysis process, chemical conversion process. In that we have transesterification to produce the biodiesel. Then we have microalgal biorefinery. So I just briefly want to touch all the points. Also, we have biochemical conversion process. So this is some say we have gasification and pyrolysis pathway. So see here, basically solid we are putting here in the starting. So we are getting the biomass and getting the charcoal. Also, you can also ask your father or no, grandfather. So initially, say in 60s, 70s, when they moved to the say Chennai or big cities, so that time there was no gas. Either you can use kerosene. Either what they do, they cut a tree, start burning, and then put some water on, make oxygen free. Then they have small pits. So like say artificial coal, you can say. And these things they carry in the cities and they can use for the cooking of food. So this is the process, we have the pyrolysis process. So in that one we can, so what they, every place they have S2, CO2 and CO. And so they get charcoal here. And then primary lipids, they are having again light hydrocarbons, aromatics, and also the olefins, CO, CO2, S2. And this is totally chemical process. We are having no microbes are involved anywhere here. So normal biomass we took it here. So you can go with charcoal, go with coke, and all the things you can produce. And now the new research that we are using, so we are using CO and S2. That is we call syngas to synthetic gas to the useful products. So also biomass to liquid. So biomass to liquid, obviously BTL, is normally referred to a synthetic fuel produced from biomass derived synthetic gas using the Fischer-Tropsch synthesis process or FTS. So the BTL technology enables production of large variety of synthetic fuels, including gasoline, diesel, heating oil, jet fuels, synthetic natural gas, methanol, dimethyl ethanol, and high alcohols. The low temperature, around 473 to 523 Kelvin, is generally used to production of jet fuels and diesel. And if you recall, there was a news that one totally biodiesel flight was from Dehradun to Delhi by SpiceJet I think before 1 year. So things are really working well here. Sorry, 1 second. Okay. The integrated biomass gasification and BTL technology progressed significantly, as one can observe from technological initiative by giant industry in the world. We see the Jamnagar, Reliance also have very, very huge, they have all the Zetropa and biodiesel. They have very good R&D centers also. A lot of companies are having. So I'm going to move this one. So I want to see one example. This is ExxonMobil. Maybe you see the ad that they have this lubricant. Develop a process for conversion of methanol produced from synthetic gas to gasoline. So this is the process they are having. So what they are having is methanol. So the methanol. Then this is they have this 1, 2, 3, 4, 5, 6 are there, and lastly they get the gasoline. So I will not go into detail here. Then we have microbial biorefinery. So the diversion of large fraction of arable lands for cultivation of oil crops is key bottleneck. See, normally what happens, see now after this Ukraine war, what happens? We are not getting the palm oils and also sunflower oil basically, okay? So normally what people say, okay, you use some oil crops that not come with food security. So the microalgae as a source of triglycerides have a potential for complete replacement of this transportation fuels with normal simplifying of the error. So normally we have ponds. In ponds we can grow algae, and algae also grow like plants only. They also need CO2 and sunlight. So rapid biomass growth rate they have, high oil productivity per hectare, high oil contents, and non-requirement of arable lands are primary reasons for such promises. So see in ponds we can have algae, and see here what happens in refinery. So see after algae we extract. So this is algae cultivation. We got the algae. See, we can see in the ponds, so blue. So then firstly, you can do dewatering. Then you can extraction, we can get triglycerides, ethanol, long chain hydrocarbons, terpenoids. Also the residues, we can go food and feed ingredients, biogas, ethanol, and feedstock. So this is how algae can be going to use it. So you can see ethanol can be also used in a lot of commoncy oxidation. You can have gasoline, synthetic gas, aromatic, hydrocarbons, diethyl, all the things. And all biomass can easily be converted to the ethanol, bioethanol. This is what happened when I was giving here, simply by decofining process. So we have oil, fat, and gas. We have R1, then separation is there using CO2 and R2, and you can have green diesel properly here. R1 is one single carbon, 2 carbon. The conclusion I can say here, the biorefinery offers plenty of opportunities to produce an array of fuels and organic chemicals from biomass. The biorefinery can be in through various biomass conversion technologies. So depending, say in Chennai, we have different. Basically, we have the rice husk is there. Also, cassava is also there. We go to Punjab side, they have more wheat is there. So depending on which region, which kind of substrates are available. If they are available to 12 months, they are available 6 months. And one more thing, see, the substrate cost is very low here. So including thermochemical conversion of this LCB through gasification and fast pyrolysis, chemical conversion of triglyceride by transesterification with methanol, and biochemical conversion of carbohydrates to bioethanol and biobutanol or HDO, microbial process using aqueous phase. So all combined things are there that can be used for biomass. The biomass gasification provides an avenue to produce range of fuels and organic chemicals through the synthetic gas, where you can use CO and H2 to gas fermentation process. The biomass gasification, however, seems to be economically viable due to the huge capital investment nowadays, but now funding is coming. The catalytic gasification is a potential alternative with enhanced efficiency, and now gets with the rapid increase in gasoline fuel price, so it's more effective now. The fast pyrolysis is promising thermochemical conversion process of LCV due to simplicity, low capital investment, and economic viability of small scale. The transesterification of vegetable oils is a potential technology for production of biodiesel. The requirement of huge quantity of vegetable oils together with their edible nature are primary bottlenecks. So see, we can use easily sunflower oil, we can easily use palm oil, but again, they are in the food chain also. So that's why we see there are some, if you go to any hilly area or in any land shows, so there are some kind of vegetable oils are there. They are not in the food chain like jatropha. So we can use those seeds. The highly productive microalgae offers a abound source of triglycerides for biodiesel. It also progresses with cost-effective harvesting. Extraction of oil from microalgae. Also, I see one picture. So when microalgae using CO2 giving oxygen, and then oxygen can use a bacteria. So together also they also treat properly wastewater. They also grow properly, so we can use both combined. The alcoholic biofuels are generally produced through fermentation of carbohydrates, of sugar, and starchy biomass. The production of alcoholic biofuels from world's most abundant, cheap, and non-edible LCB are still limited due to the high cost of production. Still, because normally still the potable alcohol demand is also more, but now seen government also adding in that gasoline also. So again, we can easily produce from the low, like say. Normal biomass also, so a lot of research also going on this one. Sooner hydrocarbon biorefinery is going to be a dominating technology. If technological advancements results competitive production costs. So in that one, same wastewater we can use any kind of we can buy farmers this all this their straw and paddy, all the things we can go to control. So here I want to conclude my talk. If any questions are there, please let me know.
Thank you, sir. Thank you very much, sir. It is a very informative and wonderful session, sir. Especially that the biorefineries part.
Yeah, actually that combined all together.
Yes, sir. Yes, sir. Nowadays the biorefineries is growing faster. Even any startup ideas is there. We'll come up with the regarding the setting up the biorefinery. Definitely, government also ready to approve their projects.
Sure.
Yeah. So participants, you can unmute yourself and you can discuss with you about the ecological and economic aspects of biochar and biofuels.
I think someone is.
Sir, excuse me.
Yes, sir.
This is Meena from RMK Engineering College. And you were talking about the biodiesel production from the vegetable oil, that is especially the edible nature is the bottleneck of the technology.
Yes, sir.
At present, they are using the used oil, no, sir?
Yeah, actually, we also.
Sir, in that case.
Can you complete the question?
Sir, that's what, sir. At present, nowadays, they are using the used oil.
Yes. Actually,
What about efficiency, sir?
Yeah. See, I'm also saying, suppose if you go eating outside, can we eat 7 days together outside? Our stomach have problem. What happens here, see in the, if you go to any hotels and all the things, they don't replace the oil. They use heating. See what happens, I'll tell you one thing about food aspect. Some oils use ghee, okay? So normally what happens, if you go more than 100 degree, it lost all calorific values. Okay. So normally we don't advise to cook in the ghee. Normally we ghee put after the cooked food. Yes. Similarly, if you use mustard oil. So mustard oil, if you go to 200 degree, is more fine. Coconut oil are the same thing. So all oils are depending. Some need some preheating, some are more heating. Now question come to the another what she asking, Dr. Meena asking. So even some research also going on. Even we also working see how this. We can collect the oil from the hotels and other things, and that can be used properly, no problem. Even cheaper rate we can get the oil. But again, if we go for biorefinery, we need regular supply is there. See, now what happens due to this Ukraine and Russia war, due to COVID, firstly, the supply chain was destroyed completely. flights are not going, ships are not coming. So supply chain. So whenever see any plant we do, see, we need one thing is supply and demand. Okay, so depending on now the government easily adding 20% of ethanol in the diesels. Now a lot of companies came. See any sugar industries now they have with sugar industry, ethanol industry together with that one because the molasses product they can directly going to use it. So, but still, and to huge demand, there is a lot of research also going on. That's why they are moving to now more microalgae also, and like some say like Jatropha. Jatropha we can grow in some land that is not used for the farming. Yes, I think one more question is there from Krishna.
Sir, you were talking about ExxonMobil, a company who's doing, you showed a refinery process
Yeah,
which ExxonMobil was using.
yes.
Sir, I would large scale industry for microalgae.
Okay, microalgae actually there are some startups coming. Actually, one of my friend also started startup in Singapore.
Okay.
And some startups are coming now, and even see if you go to Jamnagar, Gujarat, where Reliance main headquarters is there. So they are having a very huge investment on this microalgae and also in the Jatropha also, and it's really viable because growing cost is not much, and also if you have to process, it can be done easily.
I was keen in understanding the reality in, because we learn in theory, we see in research papers, but is it brought into reality? What is the yield?
Yeah, see what happens. See now, in the starting we have a lot of biogas plants, okay, and suddenly LPG was available in 2010. So the cost of LPG was much more cheaper than the biogas. So then people forgetting that one. Now again the LPG goes high, again people are moving that side. So again, depending that two products are there, so depending on that one. See now, if you go to buy the petrol pump, so we have one is in there also you have differences there. One is high octane number and low octane number. But still, see for sustainability, these things government also funding very well. Even if you have some idea, there's a coal the big BARC bark. So from Bark, I have one friend, so they give around 50 lakh funding to you. Suppose you have some idea for scale up. Okay. Suppose you want to produce monthly 1,000 kg of algae and going to do. So in that idea, you can go properly and we can, some industry surely will come. And now what happens? Now CPCB and all state governments, they are tightening the rules. Actually, if any industry, suppose if any biscuit industry is there, any distillery is there, any pharma industry is there, now rules are very strict that they have to treat that wastewater. Okay. So then if you have some innovative idea, okay, you can treat also, you can produce this algae, you can use for biodiesel. So companies will come.
Thank you, sir.
Okay, then no more questions. So I thank you all. I think one Arup Prasad have some question. Arun Prasad.
Sir, good evening, sir.
Good evening.
Sir, your presentation was very nice. Sir, still we are struggling to use biodiesel in a vehicle. What is the reason behind that, sir?
See now, you can see if you see before 5 years, okay?
Yes, sir.
E-vehicle was a very big challenge. Say before 10 years, okay, e-vehicle will not possible, it don't go one gear, and now started with the bikes,
Yes,
Ola is selling the things you can see now, and also before say 5 years, car was also not available. Now you can see a lot of green cars are there. So see what happens, see when production is more, okay, say for biodiesel compared to actually time was not allowed, I can say properly biodiesel and the ethanol and the gasoline properly together, okay. So calorific value also, so depending on the demand, see now also see there should be, when I was doing my PhD in IIT Delhi, so they actually developed a car. So in that one, they can easily go with this methane, biogas. And if you go to all metro cities like Delhi or Chennai, all cars from CNG.
Yes,
What
sir.
is CNG? CNG, what is compressed natural gas only, nothing else.
Yes.
So the process can be there, demand is there, can be modified, can be available.
Yes, sir. Thank you, sir. Thank you.
Yeah. So I think one more.
Sir, one more, participants raised the hand.
Yeah,
Sir,
please.
Jnana Sambandhan, sir.
Please unmute and ask, please.
Sir, can you please unmute yourself and, ask the question?
I think Thiru Ganga. I think.
Jnana Sambandhan.
Ah. If your mic is not working, you can type it also. In chat box, you can type it.
There was some issues. I think there was some issues on this.
Okay. So, okay, sir. Also,
So any other questions is there? Then we will go ahead, or otherwise we will, move to the, vote of thanks.
yeah, today my 12th hours is going on. I came to my conference.
Yeah, definitely. You may be exhausted. I think, still you are in the office. I could see you. Yeah. So, I request the comparing team.
Yes, sir.
Yeah, please go ahead.
Thank you, sir, for sharing your valuable insights with us. Gratitude
Yes,
is
thank you,
not
ma'am.
only the greatest of
Very good
virtues,
evening,
but the
dear
last of
all.
all others. With this,
Incredibly
I would like to
honored
call upon
and
Dr.
privileged
J.
to
Veermani,
have
Head of Department of Chemical Engineering, to propose vote of thanks.
sincere thank to our most respected principal, sir, Dr. E. Kamalanaban, sir, for grabbing this opportunity. The and hearty congratulations. Our today's chief guest is none save the Assistant Professor, Department of Biotechnology, NIT Warangal. Sir, thank you, sir.
Thank you, madam. Thank you very much.
Yes, I also want to thank all the respected delegates for taking their valuable time out and ensuring their presence here. We feel enlightened and believe that we got to learn many things from this to FDP of the day 2 session. The words would fall short of describing how much knowledge we could derive important ideas. Everyone's speech one is over. With a special mention is none other our today's chief guest, Dr. Suresh Ban Sevdar sir. Speech was emphasized as with the importance of waste to wealth. Moreover, the way he explained the topic is quite brilliant. Last but not least, I want to extend my vote of thanks to our organizing team of this ATAL sponsored ACTFDP for making this event as a more beautiful. Finally, I want to grab the opportunity to thank our beloved Dean, Dr. Rivaraj sir, Dean of Biotech and Chemical Engineering, and our continuous support Dean of Dr. R&D, Dr. B. Bharadiraja sir, for his special support this workshop, this FDP, like this in future. And together, I want to have a special thanks to all the delegates for to being the part of the program in the ways we cannot recognize. Is Gopi sir? Sir, Gopi sir?
I'm audible, ma'am.
Yeah, yes sir, now it's okay sir.
Yes. You're completed, right?
Yes sir, right sir. Yes.
So, on behalf of the organizing team, once again, I thank you, Suresh sir, for, accepting our invitation and, shared the valuable insights about the wastewater reactor design and ecological and economic aspects of the biochar and oils. So, thank you very much, sir, once again. So, for
Okay,
joining
sir,
with
thank
us.
you. Thank you all, sir, and see you tomorrow morning.
Yeah, definitely, sir. Definitely.
Okay, sir. Good night.
Thank you, sir. Good night, sir. So, participants, there was a feedback. Link is shared in the chat room, and also the willingness form for the food accommodation and traveling details also is shared in the chat room. So you can fill out both the forms without fail, so that we can able to provide the better solutions, and we arrange the comfortable stay at our premises. So thank you very much for joining today, day 2 FDP. Thank you, ma'am. Thank you very much.
Yes, sir.
So thank you, comparing team and Pavitran. So you can stop the live streaming. Thank you very much. Bye bye. Good night, all.